Afternoon. I'm a geologist, and probably for about the past month, I have been fighting a losing battle with tree pollen. So my voice and cough is going to come out throughout, and I apologize for that. But before we jump into it, I want to talk about sort of climate from a geologist sort of perspective. Stephen Jay Gould, who's a famous evolutionary biologist, said that geology's greatest contribution to mankind is the concept of deep time, or that is the Earth is very, very old, and that we have a lot of extremes that the Earth has gone through. And so what I study, or what I attempt to try to look at, is what are those extremes? And the last speaker mentioned, what would an Earth look like if it was 12 degrees hotter? Well, geologists can provide that a little bit. Maybe not what it affects society, but we can look at, see what was an Earth that was 12 degrees hotter as a global, and what was the landscapes look like. And so what we look at today in climate, and what we've seen probably a lot and everybody's familiar with, is this Keeling curve, this very famous Keeling curve. And it goes from, we have age here on the bottom, and up on the top we have CO2 in parts per million. And we've seen that, measured it directly in the atmosphere from Mauna Loa. We have these waxing and waning seasonal as the Earth's biome uses CO2, but generally going up, okay? And over the last 50 million years. But what's that mean in concept of deep time? Well, we have another proxy we can look at as fossil atmosphere, okay? So we can look at the ice cores, and we can get little gas bubbles that trap fossil atmosphere. And those show that the CO2 over the last 800,000 years has followed some cycle that is largely following orbital forcing parameters of the Earth precession going around the sun. But then here we see, this is actually February 24th reading from the Scripps Institute. We're at 401.03 parts per million, and that's clear up here. So we have completely surpassed this envelope, and that is largely what we talk about when we talk about climate change today. Okay? This is the last measurable aspect that we have of the atmosphere. So what do we want to do if we want to study something older than that? Well, we have to have a proxy or substitute of the climate. And that's largely what I look at is proxies. Now here's a proxy that I won't be talking about today, but you can take animals that create their shell from seawater, and that uses oxygen that has a different isotope, and that's what this plot is. All of these are data points of the oxygen isotope 18, and you can see the variance of it plotted at some scale over here. Okay, that scale is actually standardized. We won't go into that. But here is the last plot I showed you. And so all this variance right here is what has happened over the last 65 million years. Okay. Generally up, as we get higher, we are getting warmer. As this scale comes down, we are getting colder. So you can see there's lots of little blips and burps over the last 65 million years. Well, what I want to talk about today is soils. Okay? And really what I want to talk about is soils or surfaces that were in interaction with an atmosphere in the past that have then been buried. Okay? We call those paleosols. And so here is, and why our area is such a good place to look at that. So here is maybe a dark picture that I just took off Google of the Great Plains. Okay, so Denver, Dallas. Okay? Note that anybody who's been to Denver, there's very big mountains right here. And then we see these stream valleys coming off of Denver, forming this large gradient slope out here called the Great Plains. Okay. Lubbock is here. And we are the southern Great Plains or the southern High Plains. But there's something very specific about our plains different from the Great Plains up to the north. And that is that we are disconnected from the mountains. Okay? We are essentially this large plateau called the Llano Estacado. And so we don't have rivers flowing across, removing material, bringing material in. We're just this aggradational surface that is a good record for high climate, or is a good potential to have a high preservation of the sedimentary record. So here's the Llano Estacado right here in a profile going across here, and over here's the Pecos River. And so we have this gently sloping area, and here's the cap rock escarpment. And so we have sediment that can be building on top of that. And indeed, we do have sediment building on top of that because we have a lot of plants and agriculture going on today. Here is the modern soil map with respect to how coarse it is going from a southern location up to a northern location. So the lighter colors down here are coarser soils, sandier soils, and as you move up here, more fine-grained soils or clayier soils. Okay? That's the modern surface. We have surfaces below that that represent other surfaces that were exposed at the surface of the earth, and those represent weathering profiles. Okay, so as a surface is exposed to this, as the Earth's surface is exposed, it interacts with the atmosphere, the hydrosphere, the biosphere, cryosphere, all those other aspects that introduce a weathering profile of those sediments. Okay, and that is our soil. And the largest driver, if we can hold a lot of these things in check, is climate, and that is the precipitation or the water availability as well as the temperature. Okay? And so our model for the southern high plains is that you had these periods where you had a lot of sedimentation. So you had this sedimentation that came in, it had to come in through aeolian processes, deposited as a blanket. And then that sedimentation rate decreases a little bit, the landscape stabilizes, and you get a soil forming on there. Then rinse and repeat. You have sediment come in, create a new profile, and you get another soil profile. And that's the concept of the buried soils that we're looking at. And because those soils are interacting with the atmosphere, they have distinct weathering profiles through those buried soils. So from that weathering profile, we get a lot of crazy stuff up here. And I don't care that you necessarily read through that unless you're very geochemically inclined. What I would rather you care is you think about a soil as a bunch of minerals. Those minerals interact with water, and those minerals and the available temperature. Some of those minerals are stable, some of those minerals are unstable. The unstable minerals want to break down into the stable minerals. So if we can calculate that ratio through the chemistry, we can get at the degree of weathering. And that's largely a function of climate, past climate. And that's what these are showing up here, is a variety of tools that we use to calculate that. So what's this look like? Well, here it is, a bunch of squiggly lines going on across the screen. Okay? And the only thing that I want you to note here is that we have a high resolution sampling going up through this profile. It's about 9 meters tall of what we call the Blackwater Draw Formation, or that is the sediments on top of the cap rock. Okay? And we have a variety of soil forming horizons over here. Note, paleosols will rarely ever have the A horizon as the organics degrade down into the soil or get removed from erosion. It's mostly just B horizons for you soil scientists. And so we look at these weathering ratios and we can plot up where we think the buried soils were. And so here is our pedogenic framework of this section. Okay? So we have the modern soil that we're all familiar with and walk around that has an A horizon and we grow cotton out of, okay? Or turf grass. Okay? Here we have below that though we have a variety of buried soils. And you can see that these relate to various weathering indices as well as sometimes grain size switches. Couple things I want to note here. One, at the bottom, these two soils right here correspond to very high grain size relative to these. We get higher in grain size over here. So these are sandier. These are much more clay or silt rich. Okay? And so we think that these bottom soils represent sand sheets. You can think of them as aeolian sands moving across the southern high plains, and then it stabilizes, get a little bit of soil on there, and then sand picks up and moves across the high plains. We have very little clay in this section and very little chemical weathering in the soil profile. Okay? Whereas these upper two soils are very clay rich. They show weathering patterns that decrease down through the soil profile. This indicates more weathered, less weathered. More weathered, less weathered, or right here, more weathered, less weathered as we get this sort of trend. This here is an opposite trend. So we have weathering profiles, that is, water availability is coming from the surface down through the soil profile. And then we have this weird zone here in the middle that we're not quite sure what to do with at this point. Okay? But we kind of think that potentially why it looks so funky in here is you're incorporating some of this sandy material up within this finer grained unit as you created that across there. Okay, so if we have soils, Then we can try to characterize those soils in terms of where we expect the modern range of soils as soils develop under modern climate regimes. Now, we don't have all the horizons, so we can't do it as a modern soil scientist, but we can look at major features that they have. And so our guess characterizing these is these upper soils are mollisol. And that makes sense because the modern soil is a mollisol as well. It's in the mollisol order. And so these have features that are similar to mollisols today, absence of a horizons, right? But these down here are not mollisols. They're very sandy, carbonate rich, very weakly weathered, and so they're probably classified best as iridosols. So the first order, this is much more arid, up at the top much more dry, or much more wet. Okay, so we can take a variety of climofunctions, that is trying to take that weathering profile and add a number to it. So we do a variety of these things, and here they are plotted up together. We can't do much with these down here because those soils don't allow for that, but we know that they're dry. Okay. If we take an error-weighted average of this, we see that as we move up through buried soil 1, 2, 3, 4, we move up to buried soil 2, we are getting wetter, and then we're getting drier. We don't have a lot of age control, but we do have some specific points that are tied to some of these cycles. And I will come to that in a second. And so what we see, we think, is we have this wetting signal going from buried soils 4, 5, 3 up to 2, and then a drying signal back to buried soil 1. These correspond to age dates that we have over here. Buried soil 2 was the last time we had a reverse paleomagnetic field, and that was from 1 to 8 million years. This was 100,000 years. I also have another student who looked at younger soils, and we saw that we were much drier. This bar is the last 100 million years, if you put that on a, or not 100 years, the measured record here on the Southern High Plains. Okay, so relative to that, we were roughly in this zone. We got much wetter at buried soil 2, and then we got drier, and some modern soils, or some, not modern, much younger soils that another student of mine looked at, probably crossed over, and now we're getting back wetter again. Okay. And so I think that she's flashing at me that I'm done, and so I really just wanted to answer some questions, but then point to you that this is largely my students that did this, and I have them do that. All right, questions?
Time for some questions?
No? Sure. Yeah.
So the process, you're saying, it's a cycle of washout that brings in sand, overlay, and then soil from plant decomposition and water leads to, is that what you're calling weathering, or is it just a?
Yeah, so at any time anything's exposed to the surface of the earth, it's exposed to rainfall, it's exposed to temperature, and so that creates a regime that makes some minerals unstable and some minerals like that regime. So those unstable minerals will break down. That's what soil is. It's the breakdown of some minerals into other minerals. And so that's the weathering profile. And it depends on what is going on with the soil that you get a variety of weathering conditions. Certain soils in the Arctic are largely a function of ice products and cold temperatures. In the equator, it's a lot of rain coming down, a lot of temperature. Yeah.
Dustin, if the caliche builds up in these soils and responds to, lack of rainfall, or if you have none amount of rainfall, how many buried caliche layers do you see?
Very good. Well, caliche layers I prefer to think of it as a carbonate-rich horizon. Okay? Because if you think of it as caliche layers, that provides a different morphology. So the caprock is a strong caliche, and we don't see any of those up above, but we do see carbonate-rich horizons. What we see is there's one associated with the modern surface right here, this BK horizon. You go down through here in the buried soil 1, there's one right here where we very high carbonate-rich right here. And then we see another one down here, and then you have the caprock caliche right here. Okay? So that's what we see in this profile. At other places around the southern high plains, there's different levels of caliche profile, or carbonate-rich horizons. How's that?
So how does that relate to moisture levels?
Yeah, so it depends on sort of how you think about caliche. Now, modern sort of view is that the caliche profile is correlated to the rainfall, but it's really an effect of how deep the roots go. And so you get respiration from the plants down into the soil profile, and that controls the carbonate going down in there. Sort of, you look at a textbook 30 years ago, it was just the rain pushing the carbonate down through there. So it's correlated to wetter times, right? And so one of the proxies that we use is depth to that carbonate soil, and that provides a mean annual precipitation over the life of that soil. Yeah.
How do you differentiate between the carbonates that were formed in place and the carbonates that were deposited? And when that
Okay, so that's in this environment, there's no carbonates that are deposited except for if it's eroding from a soil profile as a wind. Okay, so you have carbonate that's coming in through wind processes, landing on, and then that gets infiltrated down through the soil. Okay, so that is not respirated from the plants. That could be something that's moving down through the profile. But I suppose if I was to try to do that, it would be carbon isotopes, but I'm not trying to do that. That's not where I'm at. I'm more looking at where do you have that calcic horizon down in the soil and noting that both happen. Now, in this terrestrial environment, we don't have carbonates precipitating from standing aqueous water in a lake or anything like that. So it would either be from soil erosion, making that carbonate move as a sand grain and then landing on the material, or from carbonate stuff coming down if it's not from soil respiration from plants.
Your section, when you have so many meters, those were not on top of each other. You had to go a certain distance in order to get the top and then move along a certain distance to the east, I presume.
10 feet.
Is that it?
Yeah, just the length of this wall, you just go up. Yeah, it's just.
And you're able to get the whole 9 meters that way?
So that's just standard sort of measuring a stratigraphic section. What we do.
They were exposed.
You just trace it out laterally. Back to your comment, the proxies I was using was completely silicate weathering. So we acidify the soil and we're not looking at the carbonate fraction in the soil. We're really looking at hydrolysis and the silicate weathering.
Just a clarification, you had a time scale on some of your latter visuals there. And so was that optimum in rainfall, somewhere around 900,000?
Yeah, well, I did, yeah.
Can you put all of that in context on a larger scale with glaciations?
Yep, I can. I didn't want to do it in the 10-minute talk. Okay, so I actually didn't bring that slide, but essentially this is the period we refer to as the Pleistocene, okay? And so the Pleistocene has what we call the mid-Pleistocene transition, which occurs right around at this point, okay? From this point on, we have the Earth's climate appear to have a beat of about 100,000 years, okay? That is related to precession and eccentricity modulating together. Prior to that, we had a beat of about 41,000 years, and that's related to the obliquity cycle going on in the Earth's Milankovitch forcing. And what that relates to in terms of the large context is that from here on, we had very large northern hemisphere ice sheets that waxed and waned. Down here, we don't seem to see that signal as much. And we had global ice and very globally cool temperatures at times, but maybe not as globally cool and not as much northern hemisphere ice as we had in this period right up here. Okay. So potentially that northern hemisphere ice could have had some aspect of relating to that growth or this transition to this wet period, and then we've been getting this drier period. Now it's important to note that soils only record half of the cycle. They record the weathering part of the cycle. So they're biased to that weathering part of the cycle. Now whether that's during the glacial or the interglacial, well, we can battle about that. People do. So,
Thank you.